Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so today we're back at this GaN Systems Class D audio amplifier. It's pretty impressive. 200 watts per side into 8 ohms. No heat sinks on this thing. It's using GaN technology from GaN Systems. So, you know, pretty darn cool. It's an evaluation card to evaluate their GaN fits, but it's also a pretty darn cool Class D amplifier. I tested it once before, and this is a follow-up video to correct a mistake I made. I did some Bode plots comparing this to another Class D amplifier, and the other one performed as expected, or as I expected. This one did not, and the phase was really crazy. So I didn't really understand that. I figured it was something I was doing wrong, but I monkeyed around with it, and I actually did a couple different videos kind of showing that. And so anyway, now I think I understand what what's going on, and we're going to jump over here. And you know what? I did maybe look at the other video so you can see the setups and all that kind of stuff, but we're going to come over here and look at the scope, and I'm going to do a Bode plot just to show you what I saw, and then I'm going to try to explain it, okay? Alright, so let's do that. Alright, and so for the setup, just a quick setup. This is the 8 ohm load, 200 watts tied to the output. The differential probes are tied to the output. Also, this multimeter here is tied to the output, so I can just a quick look see what the voltage is here, and I can quick look see what the voltage is here. So this is looking at the input voltage, which is the green, black, and red. Red and black are the two rails, the voltage rails, and the green is the common. Okay. Then I'm looking at the input voltage here coming into the RCA connector. Now I have two things going on here. When I'm using the scope to do the Bode plot, I'll be using one of these inputs. When I'm using the function generator, I'll be using the other input. So when the first thing I'm going to do is Bode plot, then after I'm going to do some discrete measurements to show you how the phase just kind of roll. Well, when you look at the Bode plot, if you notice the phase is just kind of rolling along, okay? And we'll try to explain that later. Basically, it's a time lag thing, but okay, so input here, the RCA connector. We're just using one channel, this channel over here, okay? And I'm going to zoom in on the board so you can look at the board real quick and see what that looks like. And this is a Pintec DP25 differential probe. And scope set at times 10x. It's right here. So I think that's the input setup. Now let me just zoom in on the board so you can get a good look at it. And the close-up of the board. So we have our DC regulators out here for the low voltage stuff. The input voltage is coming in right here, this connector. It comes through these cables up to this connector for our input, our Bode capacitors. These are our output LC filters, and we're just using this channel here. Now if you look right there, you can see 1, 2, 3, 4 GaN fits we're using for this channel, and then here 1, 2, 3, 4 for that channel. So very small, very cool. And maybe there's a close-up of some of those GaN fits. They're very small, no heat sinking. 200 watts per side, 8 ohms. Pretty impressive. Very impressive. Okay guys, so what we're going to do is, first I'm going to run a Bode plot, and I'm going to show you the signal I got last time and how funky I thought the phase looked, and then I'll explain why it looks the way it does, okay? So so here, differential probe is on the output. It's coming to channel 1. The input is on channel 2. That's a scope probe set times 10. I've got those things set up appropriately, okay? Then what we do is we're going to come up this applications menu and go to the FRA analysis. See, FRA. Select that. Yes, we want that. Okay, then we come up this window. Then here's the reference circuit. That shows the setup, except for I've got these things swapped, which you can do because you can, here, let's get out of that. Go to setup. See my input, I've assigned to channel 2. Output I've assigned to channel 1. So the gain is output divided by input. So channel 1 differential probe divided by channel 2. Okay, and then I've got my AWG set up. That's my generator. It's going to go from 20 hertz to 200K just because I want to go a full decade so I can show you what happens. And then we're going to do 1.2 volts amplitude and high Z. Okay? Okay, so then we're going to, we got 30 cycles. We go 45, 90. This doesn't really matter, it just takes longer to do. So 30 is kind of in the middle. That'll take long enough. I'll probably speed through that, okay? I'll probably do a 2 or 4x maybe. And then, okay, let's go ahead. Okay, I'm going to turn on the power supply, and then we're going to hit the FRA run. Alright? And I'm going to zoom in for you too. Alright, I'm going to go ahead and turn on the power supply, and we'll start the analysis. You'll hear the fan kick on. Voltage coming up. Okay, let's do it. So in the window up here, you'll see the input and output signals, and you'll see the phase difference. And here we'll see the blue showing us the gain and the red showing us the phase. And you can actually see that it's out of phase up here, but I'm going to explain this in a moment. Okay, there's 10 kilohertz, and we're coming up on 20. And you can see how it auto scaled, and look at that, the gain just drops like a rock after 20 kilohertz. And it drops way down there. Alright, so we're done scanning. Here, let me freeze that, and then I'll turn off the power supply so I can turn off the fan. Alright, now I'm going to explain the phase, the red waveform, so try to ignore that for a moment. Look at the blue one. Now what I want to do is get a 0 over here on the scale, so let's go to scale Bode plot, and on the gain let's get an offset that gives us a 0. Okay, now you can see a 0 right there. So the gain is just below 15 dB, and look how flat that is. That is just so square. If we take a measurement, we can bring up our cursors. Bring up cursor 1, and look, I'll set it right here. You can see the readout right here. 12.2 dBs, and just watch as I scan across. That is just as flat as you can. I mean, that's just amazing how flat that is. 12.2 dB, 12.1. I mean, it is within 0.1 or 2 dBs all the way out to 10 kilohertz. Now, there's 12. We dropped down to 11.97, and at 20, see, we're at 19 kilohertz, we're 11.97, and then it just drops. Look at that. That is crazy. So I'm going to leave that there, and I'll get cursor 2. And I'll put it down the bottom. Look at that, cursor 2, within 1 kilohertz, it's gone from about 12 dB down to minus 1.3. That is, like I said, it drops like a rock. So that is very square. And look at this, all the way out 20 hertz. Very square, very nice. Now the gain, or the phase, that doesn't mean anything, and I'll explain why. Alright guys, so what I've got set up is about 930 hertz going in. Well, it is 930 hertz going, you can read it there. Now, the output is on channel 1, that's the yellow one. The input's channel 2, the blue one, and 200 millivolts per division here on the blue, and 10 volts per division there. So we're seeing 350 millivolts going in and 10.4 volts coming out. Okay, now they're in phase, they look good. Now watch this, I'm going to change the frequency. I'm going to change the frequency 200 hertz. I'm going to go up 200 hertz. Okay, look at that, almost 180 degree phase shift. If I dial that down about 10 hertz to 1120, then they're just almost perfectly 180, right? They cross at the same spot. Now, let me go up another 200 hertz approximately. I'll go up 200 hertz, but then I have to drop it again another 10, and then they're right in phase. It's about 190 hertz for every 180 degrees. So, okay, we're at 1310, right? So now let's go 400 hertz up, and then we'll be off just a little bit. Watch this. We'll go 17. Okay, we're at 17, but see, I have to go down about 20. Well, it's about 30, I guess. And I go down to about 30 hertz. We're at 1.68 is what we are. And that's what that's bounced around to, 1.68. And we're back in phase. Okay, so I'm at 190 hertz, okay? Now let's just go down in frequency for fun, okay? I'm going to drop it down. Let's get some more cycles on here. And see how it's just slowly separating? We're down at 10 hertz. So we're almost, you know, we're almost at 180, not quite. I mean, so, but there's 10 hertz. Okay, now let's just go up 20. Okay, we're going to go up. There's 100 hertz. Now let's go up to that 190. It slowly merges, so right about 190, okay? Now, if we jump up about 400 hertz, okay, look at that. But now I have to drop down about 30 hertz, right? So about 560, and we're back in phase. So there's about that. Every 400 hertz, it's back in phase. And 400 hertz is about 2.5 milliseconds. So it's a little bit more time, about 2.7 milliseconds, I think, where the delay is. And that's why the phase just looks, it appears to be rolling out of phase all the time with the input signal. But really it's just the time is, the starting time's delayed. So it's at any one point you compare the two signals, they'll appear to be out of phase. Alright guys, so that's kind of cool, right? I mean, it's kind of interesting anyway. So let me explain it. It is kind of a cool thing that's happening. This guy has this, has a pretty advanced DSP on board. That's a digital signal processor. So it's taking the signal in, doing a whole bunch of stuff, and then spitting it out. And I think this guy, I can't remember how many pins it is now, it's like 128 pins. A lot of pins on this thing. So I believe this thing has 8 input ports and 12 output ports. Now, I believe what you can do with that is all kinds of stuff. You can run a bunch of different channels, bring in a bunch of channels, run a bunch of different channels. You can do equalization. So I think what that means is you're bringing in a signal, break it off into maybe, say, a treble, mid-range, and a bass, and you know, do your electronic crossover right here and pump those signals out to different amplifiers. This one's set up as a 2-channel amplifier, so it's probably only using a portion of what that chip can do, but it is doing some of the cool things it does is it can take some of the noise it might see and blend it in and clean out the signal, the noise that's coming in, so it doesn't put that noise out. So it can do a lot of different things. Now, I'm not familiar enough with this chip to tell you details about it, except for what I saw on the data sheet, okay? But it just does. It looks like it's a very impressive chip. Well, to do all that cool stuff, when the signal comes in, it takes a moment to process that. Now, you can actually set up a delay, and it has pretty wide range that you can set up the delay. But from the input signal coming in to the output signal, when we normally do these Bode plots, what we're looking at is analog signals. We want to make sure that the parasitics, the inductance, capacitance in the circuit haven't changed the phase from input to output. Something like this is entirely different. It hits this DSP chip. The DSP chip does its magic on it, and then it puts out the signal. So when it does that, there's going to be a time delay from the input to the output. Now, in a normal analog circuit, that phase shift, phase and time is essentially the same thing. And in this case, it's different because the entire signal is just held back a little bit. And so as the input comes in, the output is held back before it can go out. Okay, so it's held back about 2.7 milliseconds, I think, from what I can tell. So the input signal is just ahead of the output signal. So when we're looking here, every so often you'll get a signal that looks like it's in phase, but it just happens to be that way. It's just, you know, it's things. I was trying to think of a way to explain this, but let's just say you have two trains, okay? They're exact same trains, same number of cars, and they're both, you know, they both have a bunch of blue train cars. But every fourth one's a yellow one, okay? If both trains start at the same time, then, and let's say the front engine is a yellow car. Well, you're going to see yellow, and then so many blues and a yellow, so many blues and a yellow. And they're always going to be in phase, just lined up as they're running down the train tracks, okay? But now let's say you start the train on the left track first, and the train on the right track just a little bit behind it, like say 2 cars behind it. Well, it's going to appear that they're out of phase, but they're still going the same speed. It's just that the yellow cars never line up because of the way they got staggered on the start. But, you know, obviously, so if you start every 4th car where a yellow car appears, then that engine's going to be lined up to one of those yellow cars, and then it'll look like they're in phase, or they're, you know, in the same place, where really the one in the train on the left side still ahead. It's just that they look like they're in phase. Every time a passerby happens to see the train going by the road, he's going to see yellow car, blue car, and then yellow. You know, it's going to be, it looks like it's in phase. And that's just because of the timing between when they got started and how often you saw a yellow car. But I don't know if that makes sense. A little bit hard to explain, maybe you understand, but you know, so anyway, as far as what we care about when we do phase gain relationships in the analog circuit, we want to make sure that the inductance and capacitance, Eli the Iceman, hasn't changed our signal, kind of messed up our signal. In this case, where the output just happens to be starting at a different place than the input started, well, as far as our ears can tell, as far as the output signal goes, if we weren't comparing it to the input, it would look identical to the input, the gain and the phase, if we lined them back up again. So, you know, so that it's kind of difficult to compare. Like, this guy still has an LC filter on the output, so it's a little bit difficult to compare the parasitics and the changes, because from the very beginning the DSP has already changed that timing between the input and output. And so the phase relationship, you know, doesn't really mean anything. That's why, but on the gain of this guy, because of this processor, you can say, hey, I want to go to 20K. After 20K, boom, drop it. And that's what it did. It's pretty impressive. I mean, it's like the ideal filter. Square, I want square signal and then drop off. Now on the input, when I do the Bode plot, it only goes to 20 hertz and it's just dead flat. When I looked at the signal here, I should have, well, you kind of, maybe if you notice, when I went down to 10 hertz, the amplitude changed a little bit. So from 20 hertz to 10 hertz, it's rolling off a lot slower. And that might be because there's only 10 hertz difference, where at 20 kilohertz, you know, 10 hertz, maybe, you know, 10 hertz, you wouldn't have saw much change. But man, from 20 kilohertz to 30 kilohertz, you sure saw it change. I mean, that roll off was impressive. Yeah, so I hope that made more sense. And you know, the other videos, I know some of the guys that, you know, some of you guys wrote in, you understood what was going on, and it took me a while to catch on to that. So hope this makes sense, and we're going to do some more testing, but I just want to kind of clear this up if I did. Hopefully I did. Alright guys, hey, thanks a lot, and thanks for watching, and we'll see you next time.